In my last video, we discussed different sizes, different types of black holes. And one of these is a stellar mass black hole, which is formed from the death of a star. But for this to occur, the star must have a certain amount of mass. Well then, what happens to stars that do not have enough mass for this outcome? This is Cup of Science Joe, and today I want to talk about another end result of stellar death, known as the Neutron Star. For this formation to happen, the collapsing star must be around 8 times the mass of our Sun. And, like with a black hole, like with the normal death of a star, it first has to run out of its fuel. Now this happens after the star has fused all of its materials that during the fusion process will create energy rather than taking it up. It goes through hydrogen, helium, carbon, neon, oxygen, and ends on silicon. At this stage, the star's core is composed of iron, and no more energy can be gained from that fusion. It starts to take the energy for those fusions. At this point, the forces that were originally pushing out against the gravity of the star, keeping it in balance, lose to the gravity of the star itself, trying to push it in, causing the star to rapidly collapse in on itself before rebounding back out into space, basically going supernova. This is how we happen to get planetary nebula. Not all of the mass is lost in this way, though, and the core of the star still remains and will become something new. And as I mentioned earlier, for today's topic, that is the neutron star. While this comes one step short of stellar mass black holes in terms of mass, neutron stars are still both massive and they're dense. They're pretty small in terms of size. In fact, they are the densest material that we can directly observe. Because unlike a black hole whose event horizon prevents all light from escaping it, a neutron star is giving off its own light in different parts of the spectrum. Now, as I mentioned earlier, these objects are very dense. Imagine packing a massive star into a sphere that is the diameter of a city. If we were to have neutron star material here on Earth, a sugar cube size amount of it would weigh around 1 billion tons, which is roughly the same as a mountain. Let's turn our clock back a bit to 1967. Jocelyn Bell Burnell, an astronomy grad student who was working with Anthony Hewish at the Cambridge University, spotted a weak repeating signal using a large radio telescope that was located at the Mullard Radio Astronomy Observatory. While they entertained the idea of these being aliens, little green men, if you will, this idea was quickly dismissed. Instead, they realized that they had picked up on an unusual star that exhibited characteristics of a previously predicted object, the neutron star. Similar to black holes, this prediction had predated its discovery. It was made in 1934 by astronomers Walter Bade and Fritz Zwicky. I very well may have butchered those names, but here we are. Now, since this discovery, scientists have uncovered many more neutron stars, some with different properties than others, but they all share some characteristics. As mentioned previously, they are all small and very dense, but this is not the only trait that they share. They are also spinning very quickly. Let's imagine a figure skater for a moment spinning on the ice. When they have their arms stretched out, they will be spinning more slowly. But if they were to bring their arms in close to their body, their rate of spinning would increase. Now, if we scale this up to a star, it stands to reason that a more compact neutron star would be able to spin more quickly than the larger size star it began as. After the supernova, the remnant with its smaller diameter will come out with a much higher rotation speed. The fastest spinning neutron star that we've discovered anyway makes 716 rotations per second, which I truthfully find hard to even imagine. This brings us to something known as pulsars, which we can use as a cosmic timekeeper of sorts. You see, another trait of neutron stars is that many of them emit continuous beams of radiation from opposing hemispheres. And if the neutron star is spinning at just the right orientation relative to Earth, that beam may sweep across our planet repeatedly and very consistently. That is what makes it a pulsar. This is the class of object Jocelyn Bell discovered as two radio telescopes. They look like flickering stars in the night sky. Normal pulsars spin in the seconds range, but with the one we mentioned earlier, here's a name for you, PSR J1748-244AD, which has the 716 rotations per second, is known as a millisecond pulsar. These speedy pulsars are likely thanks to a cosmic partner in their system. If the pulsar is in a binary system, it can pull in material from its companion, which ends up increasing the rate of its spin. Typically, the radiation emitted from a pulsar tends to be in the radio wavelengths, but there are a few examples at the optical, X-ray, and gamma ray wavelengths as well. To give an example of an optical pulsar, we can look towards the neutron star located at the center of the Crab Nebula. Another thing I'd like to mention here is that over time, many of the neutron stars will slow down and lose their spin. So it is maybe even possible for something to be a pulsar in the beginning and to one day expend that energy and stop moving and no longer show up as a pulsar. And this has something to do with their magnetic fields, which we'll touch on next, bringing us to our next variant of neutron star, the Magnetar. Now, neutron stars are the most magnetic objects in space, with all of them having magnetic fields billions or trillions of times stronger than Earth's. But this can be taken even a step further. A magnetar can have a magnetic field another 1,000 times stronger than their normal neutron star counterparts. Then on top of that, you add the spin of the star, and this gives us a more violent outcome. These magnetic forces can cause starquakes on the surface of a magnetar, rupturing the star's crust and producing brilliant flashes of gamma rays that are so powerful they can have an effect on Earth's upper atmosphere, even when coming from very far away. You know, traveling thousands of light years across the Milky Way galaxy. This violent nature makes magnetars much less consistent than pulsars. So while they can emit similar pulses, there is a clear difference between the two. With a standard pulsar, the radio bursts are like a nice pulse or a ping. That's why I mentioned earlier they're really almost great at keeping time in the universe. But with magnetars, it's like a series of booms. Boom, boom, boom. And their emissions are not as predictable either. This, of course, makes them more difficult to detect. Out of the 2,000 or so neutron stars discovered so far in the Milky Way alone, only 31 are definitively classified as magnetars. We have linked this type of neutron star to another astronomical event as well, known as an FRB, or fast radio burst. These are highly energetic events, with the one in 2001 carrying in just 5 milliseconds as much energy at the radio wavelengths as the sun emits in a month. Now, this burst actually went unnoticed until we detected it again in 2007. It would not be until 2020, though, while studying another magnetar labeled SGR 1935 plus 2154, that we would learn they can send that much energy that far across the universe. In the case of this magnetar, it is about 30,000 light years away. This cemented the connection between the two, magnetars and fast radio bursts, though there is still a possibility that FRBs can be emitted by other sources in the galaxy as well. Despite how much we can learn about the universe from these stellar remnants, there is still plenty that we don't understand. We have no up-close images of them, something that is not even true of black holes anymore. We don't fully understand what their interiors are like, and exactly what forces prevent them from simply collapsing into a black hole. One thing that may help us with this is when we discover where the threshold lies. Currently, the most massive known neutron star is 2.1 solar masses, and the least massive known black hole is 3 solar masses. And while we know they have magnetic fields, we don't fully understand how they are generated or how they work. These are just a few examples of what our ever-improving technology can hopefully teach us about both neutron stars and our universe. And unlike black holes, we can directly observe these objects. So I am certain we will one day uncover more of their secrets, which to me is just another reason to be excited about our current age of astronomy. I hope you've learned something, and I implore you to step outside tonight and look towards the stars.